I think we'll just start right on time and make sure we can skip straight to the content, but I'll do a little bit of introduction. One of the things I've always appreciated about our programming languages community is the close ties between academia and industry. I mean, you can literally, see that on the slide, and so I was really honored when Evan asked me to chair this session on the industry session at PLDI, especially with speakers from Apple, from Amazon, two companies that have long supported PLDI, really long interest in programming languages and support for that work. So I'm going to start by introducing John McCall. John McCall's been at Apple for 2 decades.
All right.
Working on Objective-C, Clang, C++, and now he chairs the Swift language committee. So he'll be talking about that today. A fun fact about John is that he is an avid woodworker. And I think today's talk will demonstrate some of that appreciation for joinery, for how things fit together in this talk on balancing high and low level programming in Swift. John, please.
Thank you. Hi, my name is John McCall, and I'm going to talk today about how Swift balances high and low-level programming, especially for core features like value ownership and lifetimes. Our goal with Swift was always to have a language that could be used throughout the stack. Swift has been widely successful with application and library development for a long time, and more recently we've had success adopting Swift in lower-level environments, even in kernels and hypervisors. And today I want to talk about what we've done in the language design to make that possible. Low-level programming has fairly strict requirements, which mostly come down to programmers needing to have control over costs. For example, it's not that you can never do heap allocation in an environment like the kernel. It's that you should only do that allocation when the programmer asks for it. And they need to be able to handle conditions like allocation failure. In memory-safe languages, the language and library make a lot of policy decisions that can add costs like this. Giving the programmer control over that usually means adding complexity to the language and library. For example, a safe language for low-level programming almost certainly needs multiple array types to represent different policies for how that array is stored and owned. I've listed only some of Swift's array types here, more are necessary, really. All else being the same, it'd be nice to not need all of this, but it's really essential for writing low-level code. But higher-level programs often have very different needs. Application programming especially is prone to having a lot of redundant glue code, especially if you have to write that code all out explicitly. The performance of that code, meanwhile, is often not very important, and incurring a small overhead to make that code easier to write and maintain is very likely to be a good engineering trade-off. From that perspective, the same essential complexity that supports lower-level programming often feels more like an unnecessary burden on the high-level programmer. What we believe is that there's a solution to this conflict that works well for everyone, and I'm going to sort of spell it out here. When you see a conflict like this, you try to find a core implementation model for your language that works well for low-level programming. That means that essential complexity I described is still always there under the surface. But you design the language so that it doesn't force every programmer to deal with it up front. You pick reasonable defaults, and you push people towards acceptable common solutions that work as a sort of basic baseline for how to write code. And you can use that as the core of how you teach the language to new programmers. That gives you a lot of room to build out a more advanced feature set for the under-the-covers stuff to support the lower-level programming that you need. In this talk, I'm going to explore that in the context of 3 different interesting feature areas of Swift: exclusivity, value ownership, and non-escapable values. We're going to start with exclusivity. The design of Swift centers around our concept of value types like structs. You can declare a simple struct type like this. Every value of this type is owned by a single context in the language and has independent storage for all of its properties. When I copy the value of a variable into a new variable, like this, I have to copy all of these properties. But in return, I get something that's completely separate from the old variable. Modifying the original variable has no impact on my copy or vice versa. In short, I don't get any of the problems of shared mutable state. Now, those problems are very well studied in PL circles, so I'm not going to belabor that in this context. But suffice it to say that allowing multiple references to mutable memory makes a lot of things harder or worse in the language. Now, the fact that value types don't behave like shared mutable state is really valuable to us. We want that to be true. And it actually is true automatically for a lot of basic patterns of code. But there are places where the language needs to be more explicitly restrictive. One of them comes up with closures. Suppose I have a higher order function like this. It takes a mutable reference to an array, and as the self parameter of the method, as well as a function value as an explicit argument. I can call that method like this, passing a closure as the function value. And in this simple example, I haven't broken anything about value types. There's nothing wrong here. I've just got a closure and a separate array value. But what if I capture a reference to the array in that closure? Now we've sneakily made a second reference to the variable while it's also being used as the self argument. And I could really do anything to that array in this closure, even mutate it. This turns out to have all of the same reasoning concepts for the language as shared mutable state. In the implementation of the remove method, we now have to worry about whether calling the closure that was passed in will change the array or any of its other parameters. And this is really bad for the semantics of the language. It's also really bad for performance. If it's legal to alias like this, maintaining memory safety means giving up on a lot of important optimizations. For example, when we're passing self at I to the closure here, we really don't want to have to copy the element out of the array just to pass it. But if the closure can mutate the array, it can invalidate this element, which would mean that just borrowing the element out of the array naively like this would potentially leave the function in a state that is no longer memory safe. So the only safe option if I have this aliasing would be to copy the array, copy the element before I make this call. As a result, that doesn't really work with the kind of low-level performance that we want to be able to support for low-level programming or just in general. Instead, we have a rule that we call exclusivity, which says that mutations of a variable can never overlap with any other access to it. In this example, Swift prevents the capture of the variable from overlapping the mutation of it that happens when it's passed to the method. This all happens at compile time and has no runtime overhead. It's a simple data flow analysis, very similar to the borrow checking done by Rust. But Swift doesn't just have value types. We also have classes. The basic programming model of classes is similar to the model of classes in most traditional object-oriented languages. It's inherently based around shared mutable state. Now, because of that, because we don't like the properties of shared mutable state, we strongly encourage people to use value types when they can. But classes are still really important for a lot of code, such as their typical traditional use in a lot of UI programming. We don't want to make that code impossible or frustrating to write in Swift. That creates a problem for exclusivity. Here I've taken the previous example with a higher order function and rewritten it to use class properties. Now this code is going to make two references to the same mutable property of the same object. That's going to break value types all over again if I allow this. But the compiler can't really statically reject the code in the same way, just because the references might be the references ref1 and ref2 might be to the same object. We'd end up rejecting way too much code that's actually perfectly fine at runtime. There are a lot of ways that a language could extend a rule like exclusivity to class references. All the options on this slide have parallels in Rust, but they require dramatic changes to the basic programming model of class-based programming. People can't just write class-based code and simply read and write the properties anymore. They have to go through some extra syntactic overhead. For example, consider this very simple append to a class property. If I have to explicitly lock the object, one of the alternatives on that slide, in order to access its mutable properties, the code now has to look something like this. This would be a very unwelcome, heavyweight change for most class-based programming. And in practice, while the sort of reentrancy on class-based in class-based code can be a real semantic problem, it rarely leads to the specific aliasing issue that we're worried about protecting against in order to preserve memory safety in the language. So in Swift, we make a pragmatic choice to enforce exclusivity on class properties with implicit dynamic checks. When you read or write to a class property, the runtime checks whether there are any conflicting accesses to that exact property already in progress. That silently adds overhead to class-based programming, but allows that programming to continue written in the traditional way without undermining the basic memory safety of the language. That classes have this kind of extra overhead is something that we feel that advanced programmers can learn, and novice programmers don't really need to know about. When programmers do need to avoid that overhead, they do have several options. For one, if they can completely avoid shared mutable state, there's no need for dynamic checks, as we saw before. They can also use unique reference types, which are supported in the standard library. And we have a lot of room to explore other possibilities in the future. Let's look at another feature area, value ownership. When I say value ownership, I mean the set of rules for when and how values are copied and destroyed in the language. In this example, I have a string value in a local variable. I first add that value to an array, and then print the value in the variable. Now, I said before that values belong to a single context at once. When I add this string to the array needs to own a value to store it. But then I'm still using the string later. That means I've kind of got the same value owned in multiple places. To make that work, I'm going to need to copy the string so that I have two independent values. And on this slide, I've made that copy explicit. Now, copying a value is not free. If the value is large, copying it might involve a lot of memory operations. If it contains object references, copying it might have to do reference counting or other memory management operations. These costs aren't likely to be millions of cycles, but they could add up to hundreds, and that is enough to matter for some very low-level performance-sensitive code. Now, if you don't want to copy like this, what else can you do in the language? Well, you can either consume the value or borrow it, and I'll explain those. Consuming a value means transferring it to a different context. This is a really efficient operation. You don't need to do most of the memory management. You just sort of need to move the representation of the value somewhere else, generally byte-wise. However, it has a big restriction. The value stops being available wherever it used to be. It's necessarily a strict transfer of the value. That means you can't always do this in the language. It's not a default option that's always available. Or you might have to rework the code to make it possible. In this specific example, I can consume the local variable to add it to the array, and then instead of reading the value from the local variable, I can just read it out of the array where I just put it. But that sort of convolution isn't always possible. Borrowing a value means using it temporarily without taking away the ownership of the original location. So this is our other option. Borrowing is a powerful way to avoid copies, but it also has a really big restriction. When we borrow a value, we temporarily have two contexts referring to the same value. That runs the risk of recreating all the aliasing problems we were just solving with exclusivity. So in order to safely borrow, we have to ensure that the variable that we're borrowing from is immutable, at least temporarily, during the scope of the borrow. This is a serious problem with something like shared mutable states, so class properties and so on, since the compiler can't enforce statically that you don't have multiple references to the same property. In order to borrow from something like a class property, we need to know that nothing else will try to mutate that property during the borrow. Suppose that we have something like a standard hierarchy of UI objects, which typically have parent pointers. And suppose that we try to borrow a node's current parent for some temporary purpose. How confident can we be that nothing during that borrow will reinsently try to change this property during that borrow? As a result, borrows are also not really a simple thing that you can just do by default, because it's semantically affecting. So what should we do in the language by default? There's a clear conflict here between optimizing performance by eliminating copies or making them all explicit and maintaining the ease of use of the language, because we can't always borrow or consume, which are these efficient things that we know how to do. Making copies explicit would encourage programmers to find clever ways to optimize to avoid that. But that's not necessarily a good thing for the language. In a lot of code, a few extra value copies are unlikely to ever show up on a performance profile, and worrying about them isn't a good use of programmer time. In Swift, we don't think that's the right trade-off. Programmers shouldn't have to think about ownership unless they have a good reason to. So we implicitly pick a lot of things that have consequences for when and where copies are performed, like ownership conventions on parameters and so on. And we insert copies as necessary to preserve the naive source semantics of the program. However, since the core model that we use is based on this high-performance triad of copying, consuming, or borrowing, we can support a lot of features for explicit control in the language. Many of these features are already in Swift. Some of them are still being developed and imagined. And we think there's a lot of interesting research opportunities here for future work. Lastly, I'd like to talk about some of our more recent work on lifetime restricted values. This is an area that we're still wrestling with and would really open to ideas from the research community about it. Suppose that I want to write something like a tokenizer. I take in a string, figure out the extent of the next token, and then return it. What I've written here is a perfectly reasonable function signature if I don't really care much about the low-level performance of my tokenizer. If I do care about that performance, I've got a bit of a problem. String is going to be a normal managed value type in the language. So when I return a string, my caller is going to expect to receive an independently managed value. That token that I return needs to stay valid even if the caller throws away the original string. Depending on the implementation of string, this might mean doing extra reference counting or even an entirely separate allocation. That overhead can add up very quickly for something like a tokenizer that I might expect to call very rapidly in a loop. Now, the thing is, my tokenizer doesn't really care about the ownership of the string data, right? What I'd really like to do is just say, look, you give me a pointer to an array of characters, and I'm going to give you back a slice of that that corresponds to the next token, right? This is my low-level interface to a tokenizer. It's your problem as whoever is calling me to worry about how long that array and that slice are going to last. It's your problem. That would be a very efficient API with no added overhead for managing memory, just like you could write in something like C. Of course, in C, that would be completely unsafe. I allocate a buffer here. When I call next token. When I free the underlying buffer, token is now a dang pointer. So if I use it, I've got to use after free. And you know, this is a bug that's occasionally been known to happen in C code. Like, it's caused some consequences for a few people. In Swift, we allow this to be made safe with what we call non-escapable types. So when we define a type like UTF-8 span, we can say that it is a non-escapable type. And this means that values of the type are always restricted to some scope. When we declare a function like nextToken, we can declare the dependency relationships between its parameters and results. So here, we can declare that the return value has the same dependencies as the self parameter, since it points at the same memory. The compiler can then associate values with durations in the program. The compiler knows that the buffer is valid for this duration. The token value has a dependency on that scope, so all of its uses must fall within it. The print down here is outside of that, and so it's ill-formed. In Swift, we are still very actively developing our model and syntax for lifetime restricted types. Simple patterns like I just showed you are already in the language, but we're trying to come up with the right generalization for more abstract uses. This is a wide open research area, both for us and for Rust, which has and it continues to develop and iterate on a very similar feature. I want to very briefly drill in on one of those questions in particular. In Swift today, lifetime restrictions are associated with values. One thing that this means is that the dependencies of the value on a variable, the current value in a variable can change during its scope. Here, the array starts with no dependencies, then gains dependencies over the course of the function. This gives us a very permissive, flow-sensitive rule. We can use the array early in a way that might not be valid later in the function. In a world where restrictions are type-based instead, that doesn't immediately fall out. The lifetime restriction on the local variable array is part of its type, which is going to be the same throughout the function. The lifetimes of x and y then contribute to the inference of that lifetime restriction, but nonetheless it's expected to be the same. And so the use restrictions on the variable are the same throughout its scope. So this type-based restriction might seem more limiting, but we're still looking at making the switch. Putting lifetime restrictions into the type seems to give us a much better model overall, especially when it comes to generics. For example, we'd like the generic span type to be able to support lifetime restricted elements. Consider what that means for a type like span of UTF-8 span. Values of this type have lifetime restrictions associated with the outer span that correspond to how long that array lasts. But the values stored in that array also have their own lifetime restrictions. When the type-based restriction, we need to be able to express the fact that these restrictions are independent in a way. It's much easier to not conflate them if we can talk about the element restrictions as just part of the type of the element, rather than as part of weird dependencies on the overall span, like we have in our current model. And we think we found a way to not lose the flow-sensitive restrictions that we get from the value-based model by allowing the type of a variable to be refined over the course of its scope. But like I said, this is still very much an open problem for us, and we'd love to get more thoughts on it. OK, let's wrap up. I think I'm over time already. High-level programmers need different things from a programming language, but that doesn't mean you can't appeal to both at the same time. What you do is you build the foundations of the language with low-level programmers in mind, but hide those details by default so that users don't always have to worry about them. Advanced programmers can be supported with more narrowly targeted features that reveal the underlying model. We encourage everybody to get involved. Swift has an open source design process, and we encourage thoughts and contributions from all comers. You don't have to be a Swift user at all in order to share your experiences with these ideas in other languages. And we'd really love to hear from you. Thank you very much.
OK, thank you, John. Please come up to ask questions. I'm going to turn the other mic on.
I'll ask one since I'm close. You're talking about this split between the needs of high-level and low-level programmers. How do you deal with that in the standard library? Do you have different views of the standard library for those different personas, or do you try to make a monolithic library that works for everyone?
Yeah, we have all of these features are available in the same standard library, but we encourage people both in our API design and our documentation, all of our training materials and so on, we encourage people to focus on the really standard and more general things. So with the array types, we have a copy on write array type. That's what we encourage people to use. It even has special syntactic sugar. All the other things are necessarily a little bit harder to find because they're less privileged in the language, right? And so that's the sort of approach that we take, right?
Hi, thanks for the talk. So I was wondering, in Rust, where we have those lifetimes and had them from the start, a lot of the standard library is designed around APIs that work well with lifetimes. That's one reason why the Rust standard library looks very different from the C++ standard library, right, even when it's basically the same type. Now, Swift is you're kind of now adding this to an existing language.
Right.
So do you imagine you're going to be able to kind of keep the existing APIs and make them work well in this context? Do you imagine you will have to add make the type system more complicated to account for that? Are you willing to change the standard library? Like, what's your take on that?
Yeah, I think for certain we're having some growing pains with some of the existing protocol designs. So like, especially around collections, the shape of those APIs is very much currently like doesn't really work well for non-copyable element types. So right now it's hard to write generic APIs over those things, and and that is something that we're basically just going to have to introduce a, you know, like more refined set of protocols in order to deal with. But, you know.
Yeah. So you've introduced this notion of escapable, which kind of binds the lifetime of an object to the inherent context, let's say. So like in Rust, we have like more fine-grained control over the lifetime. Let's say if your function has like 2 inputs, we can specify which lifetime, which of the inputs lifetime should be used for the output's lifetime.
Yeah.
But like this escapable does, I don't think it has the same semantics, right? So what, like, is there any plans to like give us more fine control over like the lifetime?
Oh no, we can already actually express that sort of simple dependency already. Like you can in a function signature specify which parameter you're dependent on. Like that's basically a necessary in order, you know, to do anything with non-escapable value. The non-escapable restriction is very coarse, but it just means that like the type in general has sort of restrictions. But the restrictions are, the actual restrictions are part of the dependency signature of any particular function that you're calling. It's very similar in Rust, where Rust has, you know, I don't remember but like there's a trait that tells you that a type is not scope restricted, and like, yeah. Nice.
Thank you.
Okay, let's say thank you once again, John.